Hi, everyone. So, yeah, welcome everyone and welcome to the new students. I hope you're all enjoying your visit day. So today we have the pleasure to host Krikamol for a tea talk. So for those who are new here, tea talks are the Mila weekly seminar series that take place every Friday. And today, Krikamol will share with us some thoughts on imprecise generalization. So before handing the mic over to you, Krikamol, let me remind you all of some house rules. As usual, clarification questions will be allowed to be asked during the talk. For people in person, if you have a question, you just go over this mic here, and whenever the time is right, you'll be able to ask your question. And for people online, so this time, because like sometimes mics don't usually work well remotely, you will just have to type your question and I'll ask it directly again when the time is right. There'll also be some additional time at the end of the talk for people to ask a further question, make some comments and have a more informal discussion with Krikamol here. That's pretty much it for me. So whenever you're ready, Krikamol, floor is yours.
Yeah. Hi, everyone. Thank you so much for a very kind introduction. Yeah, it's great to be here and to meet everyone here. And thank you so much for for being here today. And I think this is also a bit quite early for some people, so I really appreciate it. Yes. Yeah. So my name is Krikamol Muandet. Currently a faculty in Germany. So before I start my talk, I would like to maybe first introduce our group. So these are our groups, quite small, but we are sort of growing. We are part of CISPA, Helmholtz Center for Information Securities. So it's a research center in Germany, which is part of Helmholtz Association. So Helmholtz Association is the largest scientific organization in Germany, consisting of about 18 research centers in Germany. Right? And we are doing trustworthy AI and machine learning and security and privacy. Right now, there's about 40 faculty, 30 postdoc, and around 200 PhD students. Right? So if you want to know more about CISPA or Helmholtz Association, just visit the website. Okay. What are we going to talk about today? Okay. Of course, the focus will be on the robustness of machine learning models. And I think it's kind of becoming the topic that is of interest in a sort of a general machine learning community as well. So the goal of my talk today is basically to try to give you my understanding of what it means for machine learning model to generalize out of distribution, right? Or something that you refer to as OOD generalization, right? What is OOD generalization, right? And how does it differ from IID generalization, right? I think that's the first thing that I want to achieve today, trying to maybe convince you of the distinction, the key distinction between IID and OOD and why it's so difficult to solve, right? And then the next goal is to maybe give you a sort of a preliminary result that we have worked on, right? Not too much into detail, so the talk will be a bit high level, so to make sure that everyone understands, right? So what is robustness, right? So let's say you're trying to build an autonomous car, right? That would be able to, to be put anywhere on the street, right? For example, this is the example of the driver or the car would see, right, in front of the car. If you look on the left-hand side, can anyone guess where this is? Exactly, very good. How about on the right-hand side? Exactly. How do you know? How do you know? Well, this is not Thai, right? This is Chinese, right? And I think now she has the ability to recognize sort of the different environment, right? But you can see just from these two images that there's so many variation in sort of in terms of like what are there in the images. And for the AI or machine learning model to be able to recognize these and distinguish those features that are relevant from those features that are irrelevant for the task, that's something that is not easy to achieve, right? This also actually becoming even more relevant in medical domain, right? I don't know if you heard about this story of Google building a tool for to screen the patient who have diabetic retinopathies, right? And then they say that they can achieve it 90% over 90% accuracy, but then when they put it on the field, basically they deploy it in Thailand as well. And they try to implement this in different clinics in Thailand. And it turned out that the model caused actually more harm than good, right? And the lesson in this is that basically when you build a models, right, you might have a metric that you care about, like the accuracy, right, that you use to measure what is the model that I should use. It may not reflect basically how the model will behave in the real world, right? In this case, you might not know what the nurse, what kind of information the nurse has when he or she use that models, right? And then the question is, um, when we train this model, we don't have this kind of information at training time, right? But then we would still want to be able to build machine learning model that generalize to a real world environment, right? So just to sort of distinguish between IID setting and OOD setting, I want to sort of give a quick introduction to supervised learning in the IID setting, but I don't think I need to say much about this setting, right? So whenever you want to solve a supervised learning task, right, you have X and Y. X represent input, let's say images, Y represent the label, right, whether or not the patient has the diabetics, for example, right? And then you would construct what is called population risk, right? So this population risk represent the goal standard that you want to optimize, right? But the problem in this case is that we don't have access to population risk, right? So you only have access to the empirical data, right? So what you do is just maybe construct empirical risk and then optimize that instead, right? So from the learner perspective, right, what the learner have is, well, I have a belief, I see the data, I have the belief that there exists a distribution that generate that data, right? There's a single distribution that generates the data, right? And the goal is clear, right? That I want to achieve the smallest population risk. But I will do that by just optimizing the proxy, which is the empirical estimate, right? And one of the most popular algorithm that we use is the EIM. Basically, as the name suggests, you just minimize the empirical risk, right? And why is it a good idea to optimize this? Because the model that you get have theoretical guarantee in terms of generalization bound, right? It's guaranteed that as you have more and more data, the model become closer and closer to the true model that minimize the population risk, right? But what happens if, let's say, we don't have IID assumption anymore, right? So when the training data, right, that you observe might differ from the test data that you're going to observe in the future, what happens is that you no longer have the fixed objective that you can optimize, right? You cannot, in the end, you cannot just use the empirical risk to construct the best model because you don't even know what is the right objective to optimize, right? So from the learner perspective, this become a harder problem. Why? Because now the learner might actually have a belief over the data generating process that can be represented not just by a single distribution, right? In this case, the belief of the learner can be represented by what I call credo set. What is credo set? It's simply a set of probability distribution. And why do the learner have this belief? Because now he cannot just say, okay, I believe that there exists a single distribution that generates the data. Okay? And this is something that people have used in the literature, right? So you have, you might actually construct a set of probability distribution that represent your belief about the data, right? And then often we use minimax optimization to solve the problem. Right? How does it work, minimax optimization? Basically the goal is that now you have believed that the data could have come from one of the distribution in this set, right? So you want the model that will guarantee to work well for any distribution in this set, right? So you want to look at the worst case, basically distribution, and then minimize the objective based on that worst case distribution, right? Yes. Thank you. Okay. Any question at this point? No, right? Okay. So I think that's the key distinction between IID and OD. In IID setting, we only have to deal with what I call data uncertainties. Data uncertainty means you only have to deal with uncertainty that come from finite number of data point, right? And as the number of data point increases, this kind of uncertainty disappear, right? You only have then to solve statistical learning problem. But in the OOD setting, when your belief can only be represented by a set of probability distribution, you have to also deal with, the learner have to deal with also the second source of uncertainty, which I call generalization uncertainty. Generalization uncertainty, what does it mean? It means that you, as a learner, have to decide which distribution, right, to choose, to pick when you want to construct your objective. In this case, for example, you pick, let's say, worst case, right? It means that you prefer worst case, right? And this is essentially the distinction between IID and OD. In OD, you have to deal with two sources of uncertainty, right? Data uncertainty and generalization uncertainty, right? So I think this should be clear from the context. And why this is different? Because generalization uncertainty could be different because it's something that will not go away if you observe more and more observation. It's going to be there, right? You cannot resolve this uncertainty by observing more and more data. You have to impose certain judgment. That's why it's become a decision-making problem.
Thank you. So one option you can have is like assuming that the distribution you are going to see is the best case, which is like the same as the training distribution, right? Within this set of distributions, there's one assumption that you can make, which is like it's the best possible distribution, which we assume like it's ID from the training set, right? The best possible, right? You can do that. And also there's the worst case, right? Which is it's the worst potential possible distribution.
What do you mean exactly by best case?
In the sense that the knowledge you get from looking at the training distribution will be more readily applied, right? It will be easier for, you know what I mean? So within this set, there's like the distributions that are closest to the training distribution, right? And which the model should do easier, right? If it's
Yes.
a statistical one. And there's the worst case, right? Where probably causal model do.
Right.
Do you think there are any potential where we don't just look at the extremes and think about other ways where we can construct ideas for the middle, or
yes, exactly. So I think that's something that people have done also. I think Andrea also have similar, Kian have similar paper on that. Yes. Basically, you don't just look at the best case and worst case. You can also look at the interpolation between these two, right? But the key distinction is that you need to make a decision, right? You cannot say worst case is better than best case or average case. All of them are equally good. You have to impose the judgment. That's the key distinction, right? Yes. Okay. So what people have done in the past is basically something that I would call precise learning. What does precise learning mean? Precise learning mean now you have to deal with decision making and learning problem at the same time. So let first solve a decision making problem, right? The learner first commit to specific distribution in this set. Okay. And usually people construct this set by, for example, looking at epsilon bar around the empirical distribution of your training data, or a convex house of a collection of probability distribution, or a set of interventional distribution that imply by structural causal models, right? So you can construct Credo set in different way, but the key idea is that first, the learner have to commit to a specific distribution. And then the learner optimize for the best model. You can use, for example, average case. Look at the average accuracy across all distribution in this set. You can look at the worst case, right? Or anything in between, right? Yes. So, but what is the problem? So the problem is that usually the one of the key assumptions that people make in the field in this or digitalization is the assumption of invariance, right? What is the invariance principle? Invariance principle say that when you observe data from multiple environments, basically they exist some sort of invariant property that remain the same across all this environment. And then if there exists such structure in the data, we should somehow make use of that invariant structure, because that would guarantee that you would be able to generalize to a new environment, right? So in this paper, as the name suggests, basically is try to essentially challenge this principle in the sense that people often assume that there exists a causal mechanism that remain invariance across environment, and then they try to use that property to construct a predictor, and that only rely on the causal feature, right? And then use that predictor to generalize, and then they can show that there's a generalization guarantee of that predictor to a new environment. So what this paper actually did is essentially they took a bunch of data set, right? And then they identify the causal feature in those data set, and then train the predictor on those causal feature, right? And then compare to standard predictor where basically just train on all feature at the same time, right? And what they found is that when you use only causal feature, right, to train a predictor, the performance of those predictor actually is not better than just the standard predictor where you train on all the feature. Right? So in some sense, this show that in most of the real world data set that they use, maybe using invariant feature is not sufficient. And the reason for that is basically that it's basically throw away all the interesting heterogeneity that exists in the data set.
So I'm just wondering, there may be a problem with their methodology, right? Because they hand chose some causal features in each task, but what if they missed a bunch of features that were actually relevant for the full causal mechanism? Because it's only the full mechanism that's invariant across distributions. There's no reason for a marginal causal mechanism to necessarily be invariant. So what if part of the issue with their findings is just that
So I
they
think it
forgot
also
to-
depends on what you mean by causal mechanism, right?
It's the
I mean, I could say the causal mechanism could change across environment.
no, but what I'm saying is that I'm defining a causal mechanism as everything that would be relevant to predict the label of interest in a structural causal model. But if they're missing some of the causal parents of Y, there's no reason why the marginal causal mechanism, with a subset of
Right.
parents has to be
Okay.
invariant.
Okay. Yeah.
So I'm
yeah.
wondering if like
Yeah,
this
yeah.
is
I think they explain the way that they identify causal feature in the paper, right? And then I think they try to be as careful as possible. I think they identify two set of causal feature. The one that they think is definitely a causal feature, and the one that they think is likely to be a causal feature as well. So yeah, right. So I think yeah. So I think my understanding about OD generalization is that basically you can assume invariance, right? But I believe that invariant alone is not sufficient. It's necessary but not sufficient, right? Because invariant basically throw away the heterogeneities, right? It treat heterogeneity as a noise, right? Not a feature. And then basically we have to bring in heterogeneity back into the process, right? And now coming back to the the source of uncertainty that I have talked about, right? So in OD generalization problem, when we don't have IID assumption, we have to look at data uncertainty and generalization uncertainty at the same time, right? That means that as a learner, we have to make decision and then learn. Right? But what is the problem with this approach, right? Um, that means that the learner have to impose certain judgment at training time, right? Because now you have a credo set that represent sort of a possible distribution. So you as a learner have to impose what you prefer, right? And this is problematic because in the context of modern machine learning setting these days, there's something that arises that I would call institutional separation between learner and the operator of the models, right? And it means that the person who actually trained the machine learning model is different from the person that are going to use the models, right? And we don't have this in the IAD setting because, you know, we represent our belief just a single distribution. So there's no decision making to be made. We only need to solve statistical learning. But when is the problem involve decision making, right? The learner lack information. Why? Because the learner doesn't know who's going to use the model, right? For example, if you're at Mila, right, you might have, oh, this set of, I think this represent my uncertainty about the test environment, for example. But, you know, I have to still make some judgment to be able to solve the learning problem, right? But you cannot solve this problem by on your own because you don't really know what who is going to use that model, right? And then the question is, how do we actually build a learning uh, procedure, right? That would allow us to incorporate the fact that there's a decision-making problem and statistical learning problem at the same time, right? What is the trivial solution to this problem? One of the most trivial solution of this problem is I would just send my data to the operator and then let the operator solve this problem. Now there's no decision making, right? Because the one who going to make decision is the operator, right? The operator have information about what is the best decision. Then if I just send the data to the operator can solve statistical learning problem, and then the problem solved, right? But the problem with this solution is, you know, in the context, of course, of modern machine learning setting, we don't have the privilege to send around the data. Let's imagine, for example, you have medical data, sensitive data, right? You don't want to share this with the world, right? And this solution, of course, exists 10 years ago. We all put the data on the UCI repository, tackle, right? And then let people take those data and then learn their own models, right? Another solution, of course, the trivial one is to just make a decision and then do a model based on your judgment and then send that model to the operator. But the problem with this problem is also that, you know, the decision that you make may not correspond to the decision that the operator care about, right? I want to give the following analogy. Let's say Danya, um, my birthday is in 2 weeks. So Danya want to buy me a gift, okay? Um, but maybe she doesn't know what I like, right? But she can make her own decision. Okay, let's say she wants to buy me an iPhone because she think I like iPhone, right? So this corresponds to this solution, right? She decide what I like, then she buy me a gift, or she can give me a money, and then I decide what to buy, right? So this is the analogy, right? Um, so what is the risk of this solution? The risk is I might end up not liking the iPhone, right? What is the risk of this decision? The risk is I have to make my own decision, right? So maybe it's appear that she doesn't care about me, because she just give me money, and then it means that she doesn't know what I like, right? So maybe I feel offended or something. Yeah. So what is the so I think the solution is what is the optimal strategy that she could use, right? So that I ended up liking the solution or the gift that she gave me, right? So there's sort of a bunch of solution in between that we want to look at. Right? And what we want to achieve in the end is that one of the solution is what she can do, you can buy me a bunch of gifts. And then I can pick the best that I like, right? So at least this will be a compromise between these two solutions, basically, right? I mean, you can buy me maybe a lot of stuff, right? But then you would end up spend more money than you needed, right? So now it's kind of a trade-off, right? You have to maybe decide how many gifts you need to buy, and and make sure that my preference is taking into account, right? That I will end up liking at least one of those gifts. Okay, and that's exactly what we want to do. We want to be able to somehow um, come up with a learning process that incorporate this, right? Not just providing a solution in terms of one model, but maybe a bunch of them, such that the operator can decide at test time what is best for them. Okay, so what we want to do is to come up with something called imprecise learning, right? What is imprecise learning? So the distinction between precise learning and imprecise learning lie in the fact that in precise learning, right, you assume that the learner and operator are the same person because you assume that the decision is made by the learner. It means that the learner have some information about the operator, so he can make the decision at training time. Right? So what we want to do is we want to say, okay, what if the training and test distribution are different, and at the same time the learner and operator are also different? Right? We want to somehow solve these two problems simultaneously. Right? And the first result that we have is the joint work with one of my PhD students and my postdoc, Anurag and Alan, and one of the intern from University of Oxford, right? So what we want to do basically is that instead of allowing the learner to make decision at training time, right? Why not just keep this credo as a belief of the learner and then learn, construct a learning problem based on this credo set, right? Not making any decision at training time. And then once you accomplish learning process, then let the operator decide at test time. Right? So that's the general idea, right? And I think one of the key distinction or the key difficulty that arise from keeping the credo set as a belief instead of just commit to just a single distribution is that if you construct a preference ordering, right, based on the risk function, right? Let's say you have two model F and G, and the learner commit to a specific P in the credo set K, right? Then the preference ordering that you get will be complete. What does it mean to be complete? It means that if I give the learner any pair of model, the learner can decide whether F is better than G or G is better than F, or both, right? But the problem with the learner whose belief can be represented by a credo set is that if you look at preference ordering that arises from this belief, it will be incomplete in the sense that there exists a pair of model that the learner cannot decide whether one is better than the other. And that's a problem because now it's impossible to identify what is the best model in that class, right? And the way that we're going to solve this problem is that, okay, instead of, so this is the example of, let's say, domain generalization setting where you have observed a bunch of data set from different environment. Let's say you have in hospital, right? And then you have observed some sample from different hospital. Each hospital can be represented by a probability distribution P. And then the credo set in this case will be a convex hull of this probability distribution. So precise learning setting, right? The learner might have a data, let's say, that come from a hospital in Europe. Right? And then the learner decide, okay, I'm gonna pick P that correspond to worst case solution. And then I solve risk minimization problem, giving this function F as a solution. And then when the doctor, use this model, maybe if the doctor come from European Union, he think that maybe this is too conservative, right? So it doesn't match with his risk awareness, the level of risk awareness or preference, right? But if the doctor is coming from outside of European Union, so this model might work well for them, for that doctor, right? So what we want to do is that for imprecise learner, instead of just committing to a single probability distribution, let's commit to the entire credo set. And then we're gonna build a model, right? That take not only X as an input, but also lambda that represent some sort of a preference of the operator. In this case, it's represent the level of risk awareness of the doctor. Right? So at test time, the doctor can say, okay, I can adjust my level of risk awareness, right, by just changing this parameter here. You sort of a model that can adapt to the level of risk awareness of the doctor. Right? But then the question is, how do we learn this model? Right? The objective function that we use. Right? Is there any question at this point? Okay. So this is the objective function that we're going to use, right? So the ingredient, so the interest will be on learning this hypothesis. Like this is a function of X, which is the input, and also of lambda, which represent the choice parameter. So the first ingredient is the risk profile, right? You have data that come from an environment, so you can compute the risk function that correspond to the risk function of each environment. So the risk profile is just a vector of those risk function. Okay. Then rho lambda is just an aggregation function. An aggregation function basically just take the risk profile and then return a risk function. Right? And this is the augmented hypothesis. What is the augmented hypothesis? The augmented hypothesis is just a hypothesis that essentially, if you condition on one lambda, it gives you one hypothesis in the hypothesis space. Right? So it's different from the original hypothesis like F that only take in X, right? This also take in lambda. This is the same. This is parameter space, and then the new stuff is the choice space. And I want to emphasize the difference between choice space and parameter space. Parameter space is something that we can identify from the data. Choice space is there just to act as an index. It represents choices. So we cannot learn it from the data, okay? So what we're gonna use as an aggregation function is conditional value at risk. So the conditional value at risk is just basically we compute the average of the risk. So let's say this is the distribution of the risk, right? So we can just look at the average of the risk for those of the risks that are above a certain percentile, basically. Right? And the reason we use this is because you have interpretable lambda. So basically, in this case, lambda represents the level of risk aversion, right? So if lambda is approaching 1, is give you a worst case solution. If lambda is 0, it gives you an average case, and any value in between represents the interpolation thereof. Okay, so it's a way of navigating the credo set, right? By choosing the value of lambda, you pick specific distribution in the credo set, right? And because now we have choice space, how do we define optimality criteria? I think in this case, the natural way to define optimality criteria is to use Pareto optimalities, right? And this is the definition of Pareto optimality with respect to lambda, right? So we want to basically find an hypothesis H such that is Pareto optimal. It's Pareto optimal in the sense that you cannot find another hypothesis in the hypothesis class that is better than the optimal hypothesis in at least one objective function. And if you look at this formulation, right, if the choice space become discrete, so this become a multi-objective function optimization problem. But I mean, in our case, we consider a general set of lambda, so it could be continuous as well, right? And in this case, we show that we can summarize, right, this objective by taking expectation of this objective with respect to some distribution over lambda. Okay, so this now summarizes the objective into a single objective, which is easier to optimize, right? But so we show that actually under some condition on Q, the solution that you get from this objective correspond to the optimal solution that you would get under this objective. Right? But this doesn't inform us anything about the choice of Q, right? Now the question becomes, as a learner, I have to choose Q in some way, but I don't want to impose my own judgment on this choice. The question is, what Q should I pick? Any idea? So Q represents the distribution over lambda, and then I don't want to impose any judgment on any lambda. Uniform, okay. Why do you pick uniform? Right, but it doesn't allow you to capture lack of knowledge, right? What you are saying is you are imposing a uniform judgment, not lack of knowledge. What we want is lack of knowledge, not uniform judgment, right? Uniform actually corresponds to one judgment, right? So basically, this is the solution that people in the field come up with. If I don't know anything about lambda, just use uniform. It's actually not the right choice of distribution, right? And the way that we actually come up with this, so I will talk about this uniform thing later, because I don't know if everyone understand what I'm trying to say. If you have two alternatives, right? Two alternatives, and then you want to impose a prior over these two alternatives, but you want to express your lack of knowledge. You cannot use uniform because uniform doesn't allow you to distinguish between lack of knowledge and uniform judgment over these two alternatives, right? So whenever you want to encode a lack of knowledge, basically we cannot use uniform distribution. And the argument that I want to make is that any distribution will not work. We will have to encode it in terms of a credo set, a set of probability distribution. Right? And the way that we pick Q is basically we're gonna pick Q in such a way that at every parameter update, right? The update will always make Pareto improvement. What does it mean? It means that the parameter update will decrease the objective or the adjective, right? Not decreasing or not increasing one of them, right? Only make Pareto improvement. And if we cannot make Pareto improvement anymore, we stop, right? Because beyond that point, we are starting to impose some judgment, right? So we learn until we cannot learn anymore without imposing specific judgment on the objective. And as I said before, I mean, this idea of precise and imprecise actually originated from the field of imprecise probabilities, right? There's a connection between credo set and imprecise probability. What is imprecise probabilities? So usually when we encode our belief about some random variable, let's say P of Z, right, as a belief over Z, then there's a justification why we should use probability, additive probability as our belief, right? So if you consider, for example, gamble, right? This gamble with a payoff F1 if Z is realized. So the argument is that if this represents your true belief, then you should act accordingly to that belief, right? It means that you should be able to come up with a fair price F in such a way that you would be willing to bet for that if that realized. So the fair price tells you how much money you have to pay or how much money you will get, right, if that is realized. And definitely actually prove that the pricing scheme, right, that you should come up with correspond exactly to the additive probabilities. Because otherwise, the pricing scheme can lead to a true loss or incoherent. Basically, there exists a sequence of bet that you are guaranteed to lose the money. Right? So if you want to avoid this kind of behavior, then you should use additive probability at your belief. Right? But this also relies on the assumption that you can identify the fair price precisely. Right? And you could imagine the situation in which basically you might not know exactly what is the fair price, but you might be able to identify what is the maximum price that I'm willing to pay for the bet, or the minimum price I'm willing to also pay for the bet as well, right? So instead of representing by a single probability, you might represent by an interval here, right? And this corresponds basically to imprecise probabilities, right? This is basically a generalization of probability theory, right? And yeah, so people call this a lower provision, right? And lower provision is the maximum price at which you are willing to buy the gamble, right? And the conjugate of this is called upper provision. Right? So in probability theory, this lower provision and upper provision will coincide, right? But this is not the case in this. And basically they show that there exists a credo set, right? For any lower provision, there exists a credo set for which the lower provision is a lower envelope of that credo set. So that means that people usually use credo set as a way to represent imprecision in our belief. Okay, so that's sort of the connection to imprecise probability. Not a lot of people know about imprecise probability. I'm not sure how many people here know about imprecise, but yeah, so that the connection. But okay, I'm almost done. Okay, so this is the very preliminary result. What we are comparing here is, okay, let's look at the comparison that we are making. So we generate a data from a bunch of environment, right? And then we look at different way that we learn, right? So the first one is, so PL stands for precise learning, when lambda is 0. When lambda of learner is 0, it means that the learner decide that we are going to use average case, right? Solution. The second one corresponds to the precise learner when the learner decide that I'm going to use worst case solution. The third one is your solution. I'm going to pick a uniform and then integrate over the uniform distribution. The fourth one is the ground truth, meaning that I assume that I know the right choice. the choice of the learner is the same as the choice of the operator. And the last one is the algorithm that we propose is allow you to learn in an imprecise way. Okay. And so this is the result, right? Okay, sorry. So what you can see is we can look at this lie as the ground truth, right? So this, what happened here is that if you look here, it means that I fix lambda to be 0.4 and then train the model at that lambda values. Right? I know this is the right solution because the choice of lambda between learner and operator basically are the same, right? So I get the ground truth here. Right? And this, this lie, the green one, right? That's the average case solution, right? So you can see that the average case solution doing quite well, right? When the lambda is close to 0, but then it's deviate from the ground truth as lambda increases. Similar for the worst case, right? So the worst case is this one. It coincides with the ground truth if lambda is close to 1, but as the lambda is moving away from that, is is performed worse than the ground truth. And what we are showing here is basically that if you remain imprecise, what happens is you're doing fairly well across all lambda, right? You pay a bit of price here, right? But if you pick, let's say, worst case, and you happen to be wrong, then you have to pay a lot more, right? That's the message, right? So if you don't know the right solution, then by imposing the judgment, you pay a lot more price if you are wrong, right? So by not making any judgment, we are not wrong, but we pay a bit of price here, right? And okay, so this is the comparison, similar comparison that we just compared with the uniform distribution. So I'm gonna skip this because I think I get my message across in the first plot. So this is the experiment on the real world data. You see by sharing data. So yeah, so the task here is we predict the number of hourly bike rental from various weather related feature, right? And then we partition the data by season and year to create different domain, right? And here what we observe is that basically if you look at the ground truth, this is the ground truth. What we observe is that we can actually even do better than the ground truth. This is quite surprising at the beginning, but actually it makes sense because the worst case solution is actually very hard to learn, right? Because you are computing the average at the tail of the distribution. And at the tail of the distribution, you have very little data, right? But what we are doing is that we're learning augmented hypothesis. It means that it's kind of, there's a sharing of information across different lambda. So there's some sort of a transfer between maybe the lambda at this value and then lambda at this value. So effectively, we can use a lot more data when we learn this solution. Lambda of, so you have a bunch of domain. You have a risk profile, and you compute CISPA. So you can compute any value of CISPA, right? So I think it's hypothetical in the sense that we also have to decide what is the real lambda. Yeah, it's just the oracle values, right? Yeah, so I think, so the way you would interpret this is that, let's say if lambda, so if you look at 0.8, right, that would correspond to the oracle values, but then the algorithm that you look at use different value of lambda, right? So this is the worst case, average case, ground truth, right? When lambda is the same, when lambda is 0.8, right? And then this is sort of uniform distribution. This is the imprecise learning, right? Yeah. So yeah, that's the preliminary result. What is the takeaway message? Right? So the takeaway message is that learning in non-IID setting involves not only statistical learning, but also decision-making problem. right? And in this case, the learner have to deal not only with data uncertainty, but also generalization uncertainty, right? And the way that we solve this problem in precise learning is we assume that the learner can make that decision at training time, right? The learner has to simultaneously decide and also learn at the same time, right? This might also correspond to the setting where there's alignment between learner objective and the operator goal, right? And you might say this is why people say you should always work with domain expert when we solve some problem, right? Machine learning engineer need to always work with expert because you have more information about what the operator want, right? But I think right now, to make machine learning more practical, I think we have to deal with the institutional separation problem, right? There's always a separation between the learner and the operator of the models. And this requires to rethink the way that we build machine learning model, because as the learner, right, you're not saying we have the fixed objective, but the learner himself have to be strategic about what is the right objective, have to somehow hypothesize what is the right objective to optimize, right? So it's become now harder problem to solve compared to IID setting. So the imprecise learning allow the learner to be essentially maximally non-committal, right? Not making any judgment. And this allow the alignment of the objective of the operator at test time. So that brings me to the end of my presentation. Thank you very much.
We have a bit of time for questions, if there are some. Someone was asking online, what's the relationship between generalization uncertainty and epistemic uncertainty?
About between generalization uncertainty and epistemic. So you can think of it as a epistemic uncertainty as well. So we avoid using this term because sometimes people use aleatoric and epistemic uncertainty to refer to different things. So we use this generalization uncertainty just to make sure that we refer to the right thing. But I think you're right that it actually can be understood as an epistemic uncertainty as well.
Susan, yeah. I'm wondering if you could clarify the relationship between imprecise probabilities and, say, hierarchical Bayesian methods. Like, for your task, that's what would occur to me to try.
Right. I'm not an expert in maybe hierarchical models, but okay. I think that's one way of, dealing with. So your question is,
so
what is it?
If you go back a few slides, we can make this more concrete. Here, right? So here you have a probability, right? And you're trying to avoid having a point probability. So I can express a prior probability on that, right? That's my hierarchical Bayesian kind of expression of uncertainty about that point probability, right? So why not just use that framework?
I think you can use, there's some argument of like people that say, so the difference between using imprecise probability and hierarchical perspective is that in hierarchical perspective, you could say that I believe there exists an ideal probability distribution, but I don't have the capability to precisely measure that probability, right?
Yeah, that's right.
So you have uncertainty over that. But in imprecise probability, the way that they represent uncertainty is by a set of probability distribution. It means that you're modeling, you may not have ideal probability, right? You may not know exactly what are the ideal probability. For example, this has been used to model disagreement between experts, right? And this disagreement could happen because there exists no ideal probability distribution to begin with, right? So I think that would be the key distinction, because in hierarchical modeling, you still assume there exists some ideal probability.
Yeah,
but
that's right, actually. Yeah.
But yeah.
Good, thanks.
Thanks.
Someone is asking online how imprecise learning is different from meta-learning.
It's different from?
Meta-learning.
Meta-learning, okay. Maybe someone have to give me an idea of what meta-learning is, because I've been trying to understand meta-learning for many years, but I haven't actually managed to understand. But I don't know the answer because I don't have a good understanding of meta-learning.
Maybe Sabyasachi, you have like a more precise, like ambiguous feature of meta-learning that makes you think it's
Hi,
not
am I audible?
imprecise learning.
Hi, can you hear me?
Yeah, if you have a mic, you can directly take in it.
Hi, am I audible? No.
Yeah, it's not working. So if you can like type a more precise question, we can read it out.
Or imprecise question.
Yeah.
Question is too imprecise.
Sorry. Any other question in person? No. Okay, I'll just wait for Sabyasachi to give us further details.
Oh, there's a question over there.
Yeah, feel free to go on.
Hi, thank you for the great talk. I was curious to know if this sort of framework and these theories can be applied to cases where the underlying data distribution is actually evolving over time, and there's uncertainty in what it might be in the future, and whether we can still use, these ML models for future unknown distributions.
Yes, I think so. I think we have, I had this discussion with Rong as well yesterday about sort of maybe when you have this uncertainty about the right distribution, right, over time, what you have to do is maybe to adapt your belief, your uncertainty about the actual distribution, right? It could, for example, you could, over time, your credo set could shrink or expand depending on, the level of uncertainty you have about the environment, right? So you're not going to have the same distribution over time, right? You're going to have sort of the set of distribution that adaptively change over time, right? Depending on the problem that you're dealing with. So in that case, you could, I could say that you can add time component to the objective that we have, and then somehow modify the objective in such a way that it's taken into account the fact that the credo set can change over time as well. Yeah. Sarah?
Just a naive question. Is there any connection between these imprecise learning and Gaussian processes? Or like
Gaussian processes?
Learning a set of distributions or functions.
Right. So Gaussian processes is a distribution over function. It's just a single probability distribution, right? So imprecise, basically you have to talk about a credo set, a set of probability distribution. Now the question that you asked maybe whether we can construct an imprecise version of Gaussian processes, for example. Right? And I think that there's a lot of discussion about in the context of maybe uncertainty quantification for deep neural network as well. How do we encode or distinguish between different kind of uncertainty like epistemic or aleatoric uncertainty in deep neural network? Because right now, we don't have the effective way of doing that, right? Yeah, tell me if you have a solution. Yes.
Yeah, thanks for the talk. So yeah, my question has to do with so the first problem that you showed at the beginning with like two different images from different cities. I guess my point is I don't think we can model this kind of out of distribution with like just taking convex combination of distribution, right? So for me, this kind of extrapolation is as more to do with like being out of support than being like some kind of mixture of other distribution. I just want to have your
yeah. I think that's a good point.
Yeah.
That's a good point about extrapolation, and I just want to point out that there's more to uncertainty than probability theory. And you can look into possibility theory. So, I mean, the reason that probability theory is problematic is because let's say you have 10 classes, right? You want to build a model that make prediction about these 10 classes. So typically you assign probability to each classes. And because the property of probability is that it has to sum to 1, you are making an assumption that everything else has 0 probabilities. There's no possibility that the model would generalize to another class, right? But you could actually model it with using possibilities theory. You just say that, you know, there's a possibility that this image belongs to this class, right? You're not saying anything about whether this, so the possibility doesn't have to sum to 1. So it means that you're not making assumption that everything else has 0 probability, right? Or 0 possibilities. So that would correspond to extrapolation. And I think the point is about convex set is what I want to point out is that when I talk about preference ordering, if you have a set of probability that is not convex, you can always construct a convex house, right? And this would give you the same preference ordering as the original set. This means that if you represent behavior of the learner that arises from the belief that can be represented by this critical set, it doesn't matter whether it can be represented by a convex or non-convex set of probability distribution, because they imply the same behavioral disposition of the learner. The learner have the same behavior regardless of whether it's convex or non-convex. Yeah.
Thanks.
Yes.
Okay. I just want to follow up on this point about going out of support, because like we as humans do quite a bit of extrapolation, zero shot, and it's you know, what does that mean? Is it that like there really is something that's completely out of support, or is it that like at some level of abstraction that's more appropriate, we actually are within the same support? Like in the case that you showed with the pictures, right? Like at the end of the day, the pixels looked very different, but maybe we as humans know how to abstract all these objects into types, and we can say that any other new city will still have all the same types, but maybe just instantiated completely differently. And this kind of thing might help us to do some kind of extrapolation to an operator that you think you've never seen before, but actually maybe does kind of live within some sort of convex hull, so long as you figure out how to get the right abstraction.
I think the difficult part is to figure out that type things, right? In the end. So I don't know how to solve extrapolation. I mean, if you have images of a cow on the beach and then a cow on or a camel on the beach, or this, well, cow on the beach and cow on the sand, right? For example, well, cow on the glass, green glass, and cow on the sand, right? Those are two, you know, observation. But there could be much more observation out there that, you know, we don't know about, right? Yeah. And I don't know how to solve this problem, because I mean, how are you going to extrapolate to scenario the model haven't seen before? Because yes, I agree. Yeah.
All right, so we'll officially end the talk. Let's thank again Krikamol.
Thank you.